Welcome to our presentation on the development of a design for the production of energy from the sea. Our team is Jane, Rahat, Andrew, Jay, Hector, and our team leader, Jonathan. The main objective of this project is to produce a viable concept for a device that is able to harness energy from the sea. The most up-to-date materials and technologies will be used to showcase the potential that producing energy from the sea has as a renewable energy source. We will ensure that the environment and all interested parties are key to the development and design process, which will give a final product ideal for all interested in the design. Initially, the design started off as a combination of wind, wave and current energy installed in a system that would also act as a harbour wall. After the initial research, we found out that it would not be possible to combine these energy systems, as it would require two cables to connect the system into the grid, making the design not financially viable. As this idea was discontinued, we carried on with the idea of a hybrid system, but dropped the wave power system. This resulted in the creation of an idea for a portable turbine that could be moved round to an area where and when it was needed, ideal for offshore construction projects and disaster relief. The next slides show the results of our research. The first step of the research was to look at the interested parties. These are the investors. Large developments such as offshore power systems require a large amount of capital investment to fund the research and development of the product. Their main aim will be to gain a high return on their investment. Customers. The main customers for this system will be offshore construction companies who will work in remote areas building oil rigs. The other will be international aid organisations such as Hope Worldwide and the Disasters Emergency Committee, who aim to provide energy quickly to areas which have suffered natural disaster. Governments will also be an interested party as both customers and also as an investor, as they provide subsidies for renewable energy production development, which will go alongside the money from the investors. Local inhabitants. Anywhere where the system is installed will have effects on the local residents. In the situation of disaster relief, it will be focused on the provision of energy for hospitals and the rescue operation. But considerations will also need to be made for the local environment to ensure no more damage will be done. Any installation at sea will have to be protected from other shipping with buoys and warning lights, within the regulations set out by the International Maritime Organization. Wave terminators absorb the energy from the wave, leaving the wave behind with less overall energy. There are two main types of these. The Salter's nodding duck, which is a unit that contains a swinging pendulum connected to a generator. They sit in a line facing the incoming waves. At their maximum efficiency, these can turn 90% of the wave's energy into mechanical energy. The other type is an overtopping terminator, where the waves are drawn up a ramp into a reservoir, where the water is stored and then released through an outlet which has a turbine within it. Both these systems are extremely efficient at transferring wave energy into mechanical energy. Underwater turbines have been in use since 2003, but are still used as a singular system as they are still in development. They are able to take energy from both the tidal stream and waves. The current design of these is very similar to that of a wind turbine, but it is placed underwater. Installation of these devices is very high cost due to the foundations that are needed to support the structure under the pressure from the current. The current flow at some river mouths is large enough to power whole cities, if harnessed properly, and since it is a regular 6-hour energy surge, it can be guaranteed to last into the future, making it both a renewable and sustainable energy source. These turbines do have some negatives, as they have some environmental impacts. The blades disrupt the water flow in the area, which affects vegetation growth on the seabed, which can affect the fish stocks in the area. The materials used to produce the wind turbine and the underwater turbine differ slightly because of the different conditions that each is put under, such as any materials used underwater will need to be corrosion resistant from the seawater. For the underwater turbine blades, we narrowed down 3 materials: thermoplastics, carbon fibre and E-grade fiberglass. The main problem is the effects of UV light on the materials. As with thermoplastics, it causes the material to deform and change the shape of the blade. After looking at the tensile strength of the materials and the cost-to-weight ratio of the last 2 materials, we found out that E-glass was the ideal material for the blade. For the wind turbine blades, we took the same 3 materials, but looked at data that has been found from other construction projects of wind turbines that have been in use for a longer period of time. From this we were able to see that carbon fibre is the most commonly used and easiest to maintain material, so this will be the material that we will use for this construction project. The nacelle is the cover for the gearbox and generator of the turbine, and is vital to protect the working parts from corrosion, so the materials are very specific. The wind turbine will use a coated steel alloy, and the underwater turbine will use E-grade fiberglass. Wind turbines convert kinetic energy from the wind into electrical energy using a gearbox and generator. There are two main types of these turbines. Horizontal axis turbines have all the generator and electrical systems sitting at the top of the tower with a housing that swings to face the wind. These are most commonly used turbines currently. Vertical axis turbines use a blade system that sits vertically on the tower with the generator at the base. It is able to work at all angles of wind without twisting. There is also a new type of design, the wind shear turbine. This design is able to capture wind at any speed above 2 miles per hour. The captured wind is then funneled through a duct where it picks up speed. The wind's kinetic energy will then drive a generator at the ground level and produce electricity. Any residual wind will return to the environment. It is able to produce up to 6 times more energy than a traditional horizontal axis turbine. Due to the fact that the generator is now mobile, it needs to be able to distribute power anywhere in the world, while still meeting the safety requirements of each energy network it is connected to. The main issue is the frequency of power generation, and that a generator cannot be changed once it is installed. This means that the only solution is to rectify the power to DC, and then invert this back to AC using an adjustable inverter. This will allow the frequency to be adjusted to match that of the network. There are also a number of regulations that the connection must apply with, such as ETL 113, that means it has been approved to G59/2. This requires that all electrics must be installed in a watertight steel sheet enclosure. There must also be a lockable isolator relay system, which complies with G59/2 relay regulations. From all of the research we have come up with a basic design for the system. It will use the shear wind turbine for generating energy from the wind, whilst a twin swan turbine will sit under the water and generate energy from the underwater current and some wave energy. In order to start visualising the design, we created a number of sketches developing the float system to the final design of a semi-submersed catamaran hull similar to the design of a swath hull currently used on ships. This will have a pump system on board that is able to adjust the waterline of the hull to make it more stable in rough seas. When looking at the electricity conversion, we decided to place it off the vessel to decrease the weight of it. We have created 2 separate steel containers that can be placed on the shore as a modular system and contain all of the systems needed to run the electricity transformation. As a development to the swan turbine, we have looked at a variable pitch propeller system. This will allow the blade pitch to be changed depending on the speed of the water. This will be measured using a separate smaller propeller and will be operated by a control system. In order to control the progress of our project, we are using a Gantt chart, where individual members' work is shown and the team leader is able to monitor the progress of each team member along with the whole project. For each task there are 3 colours. Red stating the planned start and duration of the task, green showing the amount of completed work, and yellow showing the outstanding work. This Gantt chart shows the work from term 1, which is all the research and design work that is carried out to form this presentation. We have created a second Gantt chart in order to plan the next term's work. This will revolve around the development of a final design for the product and the production of a final report for the project.